Right, let's start recording. And share the screen. Let's hide controller. All right, so good morning, everyone. We are here for the 7th lecture. We will continue with indexing genomic data. This is a very important topic, so we'll spend maybe 2 to 4 lectures on this topic. This is very important for indexing and seeding. Whenever we discuss indexing, it's exact same algorithm as seeding, so please pay attention to that. The only difference we said last time is where we store whatever we got from the indexing, we store it somewhere in a data structure. It could be hash table, it could be database, a tree structure, whatever you like, right? And we discussed last time how we can query the planet, which is everything we know about sequencing data, which is the SRA database. So we agree that we need something like that. Google search for all DNA data. Again, this is not something real. We don't have such thing, but we start seeing some efforts. So we already saw Logan, which is the initial, one of the best, I would say, effort where we index the entire SRA database. And then we go over multiple of those tools and discuss the indexing size, the indexing times, and how it's different based on the algorithm that we choose for the indexing and seeding. And we agreed last time that we had already multiple options. It's up to us which one to choose. We want to go overlapping, non-overlapping, spaced, and so on. And we will pick a few of them, the very important ones, and try to go over them in detail over the next lectures. Last time we discussed the overlapping seeds. We saw how this problem still exists. So we have very similar sequences. We made only a single difference, but we still get a bunch of those seeds does not match at all. And we still see the exact same problem even if we play with the parameter value. So we increase the K value from 4 to 6, and we still see 6 of them now do not match at all. Also, the problem or the story still persists for the other side of the story, which is when we have totally different sequences. They are not similar at all. But because we have some repeated region somewhere in both of them, we could get false matches. And those false matches do not represent the similarity. So even if we quantify them and we try to say like we have half of those seeds match each other, does not mean anything. Does not mean the sequences are similar to each other. Okay, it could be by just random, by luck, we got those chances, or it could be we have just repeated region somewhere. For example, here toward the beginning and here toward the middle, we had the exact same region. But when we look at the entire sequence, they are not similar. Okay. Now let's see more sophisticated algorithmic method, how we can extract seeds out of the sequences and try to index them and then use the exact same seed for the seeding process to query that index data structure. The second method, so the first method was overlapping seeds. The second method for today called winnowing, which is the original name coming from natural language processing. And as I said, there are a lot of things happening in bioinformatics. They are copied from somewhere else. Okay, they are not original. They were not invented for bioinformatics. They were used in somewhere else. And remember, everything we do in bioinformatics at the end of the day is just text, right? So we convert those chemical molecules into ACGT data, which is a text by the end of the day. And then we could use whatever algorithm we use for NLP, because again, NLP is text, right? Could be the alphabets of English, Arabic, Chinese, whatever language you use, right? And most of those algorithms that works in text still applicable to the genomic text or genomic data. So the original name called winnowing, and what we call in genomic as minimizer seed. And you can see from the meaning of both words is exactly the same thing. We are trying to filter something out of something, right? So winnowing is this process. So farmers used to filter some of the unwanted things from the seeds after they harvested, right? Could be some dried leaves, could be some insects, could be some random stuff, right? So we winnow those stuff and filter them. The bad thing, the wind will blow them off. So they will be removed and only the seeds or the useful thing will stay there, right? And that's exactly what we are trying to do for minimizing or minimizer seeds. And this is the original paper. It was published in 2003 for NLP again. And we copied the same concept for genomics, okay? This was used for documents. Imagine you have a PDF document, another PDF document, and you'd like to check the similarity. Or you would like to just query something inside the PDF document, right? So they extract what they call as a fingerprint. And those fingerprints are basically the seeds that we extract from the document. We store them somewhere. Whenever we had a query, we extract something from that query, and we check with those fingerprints that we store somewhere. All right. Now, what is the goal? I already mentioned that, so it should be very clear. The goal is that we can extract all overlapping seeds, but their number is huge. Do you remember what was the number of overlapping seeds? Assuming the sequence is n, the entire sequence, and whatever we extract here is k, and we extract overlapped sequence, right? So all those overlapping, whenever we have a character here, we extract the next k character. Excellent. N minus k plus 1. And why we did that part? Because toward the end, k characters, we cannot extract more than 1k. Because if we go to the next overlapping seed, we don't have any character over here. So it will be less than k. That's why we deduct k, and then we add 1 to account for this character. Okay? All right. And this number is really huge. This number of overlapping seeds is really huge. Think about a read coming from nanopore technology. Do you remember nanopore technology we discussed? What was the maximum length we could get up to today? 4 million character long, right? So this could be 4 million, really. It's something huge. So 4 million minus whatever k normally is somewhere between 15 to 25. So it's still 4 million, right? So that's 4 million pieces should be indexed. And that is if you are indexing a read. If you are indexing a reference genome, human genome, that will be about 3.2 billion character, billion, not million, right? So that is something huge. And now if you would like to index all viruses that we know, good luck doing that, right? So that is the main goal of this work. So we would like to not use the entire set that we have here. We would like to use subset out of that, right? So that's the main goal of minimizer, find a smaller set of seeds to represent a subsequence, okay? How we do that? Very simple algorithm. Please pay attention and we'll get an example next slide, okay? Extract all overlapping k-mers, okay? So this is still overlapping algorithm, right? What is new? Impose an ordering on those seeds. So you would like to order those seeds. You would like to say something that this is should be first, this is second, this is third, this is fourth, okay? Those orders could be lexicographically. What does it mean, lexicographically? Lexicographical order means the alphabetical order, okay? However, because this is a text, I should throw this away. Because this is a text, so we cannot just sort based on the first character, right? So if the first character is A, then this should be the first piece. However, if we have multiple start with A's, right, we should look at the next character. If this is A and this is C, which one should come first? This one, right? Because this starts with A, and A precedes the C, okay? And vice versa. If we still have those A, we continue doing the exact same thing. But if we have here T, then this is A still coming earlier than the T, okay? Or another option is to hash the entire seed. And do you remember the hash function we discussed last time? So the hash function will convert the text into what? Numerical value, right? A number, right? So that number you could sort based on that number instead of the text, okay? So if this is 100 and this is 5,000, then the 100 is smaller than 5,000, then this is first and this is second, okay? So we just try to impose some kind of sorting or ordering in order to say, okay, I would like to pick the first, regardless. Just give me the first. I don't like the others. Or give me the first two, the first three, or the last one, or the one in the middle, okay? Based on this sorting, I'm going to make some decision to pick some of those seeds, right? Now, because I sort them, I don't want to consider all of them at once and pick only the first and ignore all the remaining. Imagine we have 4 million pieces, right? I don't want to pick the first one and ignore the rest. So I'm going to divide them into groups. And this group is recognized by W. So each group, I call it W, okay? And now this group could be overlapping, could be non-overlapping. So I could divide this W, next W seeds. I'm talking about this number of seeds, okay? N minus K plus 1. I'm going to divide this number by W groups. Or each group size is W, okay? Not W group, sorry. Not W group, there's a big difference, okay? I'm not going to divide this into W groups, but I'm going to divide it into groups, and each group size is W, okay? And I'm still maintaining the exact same thing we discussed about overlapping seeds, okay? So I have overlapping seeds, and I group them into groups. Each has W overlapping k-mers, and then out of that group, I'm going to choose something. Out of that group, I'm going to choose something. Now, what I'm doing, why I'm doing that? Think about, I have this large number. I divide into groups. Each group has W k-mers inside. And now I'm going to choose one per group. And then I'm reducing this huge number into something way smaller than what I get here, okay? Hopefully the things will be more clear with the example. So I like the practical side of this course. Now, what kind of benefits we will get? As I told you, you try to filter something and use smaller subset out of it. Now, minimizer-based approach guarantees finding at least one seed in a group of W k-mers, okay? Known as windowing guarantee. It means in every group, I'm going to get at least one seed, okay? Now, what does that mean? It means if I'm comparing two similar sequences, it's guaranteed to find the similarity between them because I'm going to get, by the end of the day, a group of representative k-mers that I can use for the comparison, okay? So although I'm using some kind of filtering, so what we mean by windowing guarantee that it's hard to not get k-mers out of a sequence, okay? It's hard to not get k-mers out of those groups. If I'm not getting k-mers at all, or if I miss some of this group, like a large number of this group, then at the end, I'm going to miss the query itself, okay? So I will not find the query in the index, although it exists, okay? You got it? We will see an example now. Okay. Let's calculate the minimizer seeds for the following genome sequence using lexicographical order. Okay, remember what's lexicographical order? We go with the first character, we sort it alphabetically in ascending or descending order. It's up to you. You could define whatever mechanism you would like to use. Okay, and the K value is 10. Remember, what is K? Is the size of the k-mer, the size of the subsequence that we extract. And W is 5. What is W? Number of k-mers within a group, or the group size. Okay, how many k-mers per group? It's not the number of groups. We are not going to divide this number over 5 groups. No, we are going to divide it over groups, whatever those groups are. Okay, but each group should have at most 5 k-mers. Why at most? Why not exactly 5? Remember, we always have problem with toward the end of the sequence. We cannot guarantee that we have exactly 5. But all of those will have exactly 5, right? Toward the end, we don't know how many remaining k-mers will be there. All right? So this is the sequence. What we will do, just go extract k character, which is 10. So give me the first 10 character, right? That's the first 10 character, k equal 10, and continue doing the overlapping algorithm, okay? So going to extract all 10 mers, 10 mers. Why 10 mers? Because k equal 10, and we're going to replace the k with 10, and then we call all of those 10 mers, okay? Now, that's exactly as we are doing an overlapping algorithm. Nothing new. But now, the new things that we are going to consider every 5 or every W k-mers individually, okay, separately, right? And in the minimizer algorithm, they choose to do this windowing thing as overlapping as well, right? It's up to you to consider the W non-overlapping. For example, this is the first group, and this is the second group, this is the third group, and so on. But they decide to do it overlapping, right? So we are going to choose 1, 2, 3, 4, 5. Yeah, that's 5. And then we skip 1, and we consider the next 5. Okay, this way. All right, now let's go back to the first window. All right, so we choose 5 k-mers. Now what? What is next? Now we need to sort them lexicographical order. Okay, let's see how we do it. Now, we use just English alphabets, right? So the first character should be A, and then B, C, D, and so on, right? Which one starts with A? Luckily, we have only one option. So that should be first, okay? And then we choose the first one all the time. Out of the W k-mers, we choose the first, which is this one. And then we pick that one. We pick that one. And that is the only one will be stored in the index. We ignore all the rest k-mers within that W window, and we keep only the first in our sorting or in our order. The order we use, just lexicographical ordering. And why we have the allocation as 0, not 1? We discussed this last time, right? In computer science, 0 is a thing, right? We consider it as a number. That's why the first character is indexed at 0, 1, 2, 3, 4, 5, and so on. Okay? As simple as that. Now we continue, or we move ahead with the next window, which is again overlapping. So we just skip the first k-mer and we continue with the rest. Now, when we ignore this and it was first, now no longer first, we need to sort again. Okay? Consider those W k-mers, and which one starts with A? The last one. Luckily, until now, we don't have 2 k-mers starting with A, right? It's easy for us. So let's pick that to be a candidate stored in the index. And what would be the location of that k-mer? It's hard to track, but let me help you. It should be this one. Then 0, 1, 2, 3, 4, 5, right? So we should store that k-mer with a location 5, right? Very simple. And the nice thing out of this algorithm is the number of k-mers that we extract is very small. Now we move on with the next window. We skip this k-mer and we add one more. Now we start having two k-mers starting with A. Okay, let's see what we will do. So we have those two within the W window, right? And both of them start with A. What should we do? We proceed to the next character. Now, next character. This is A, but this is C. Which one? A is before C in the English alphabets, right? So we choose this one as number 1, and this is number 2. And our algorithm just considers the first one. We don't care about the second, third, fourth. So we just take the first one, which is this one. Now, what is the location of this guy? 5, because it's the same one we choose. Now, if it is exactly the same thing, no need to store it again. It doesn't make any sense to store it again, right? Because we already have it. And we have the exact same location, the exact same seed. So just ignore. Nothing will happen. Now we move to the next window. So we ignore one from here. We add one from there. Now we consider those 5 candidates. And luckily, we still have those 2 as 1 and 2. And then which one is 1? This one. So we choose it again. Already stored in the index, ignore. We move to the next window. We're still getting more C's. So I think we will ignoring all of those, right? Because A is still coming before anything else. So nothing stored. We got the T, also will be ignored. Oh, one important thing. What happened? Let's go back. Now, when we arrive to this area, we are going to ignore this guy. We're ignoring the one we are storing, right? It's no longer, it's outside the window now. So we are shifting by one step. And by ignoring this one as outside the window, now we are here. Now, which one starts with A within this window? This guy, right? Now, this guy, the only one starts with A. And what's the location? Should be 6, right? So that one was 5, and this is 6. Now we are going to store what we got, right? This is one of the most famous algorithms in bioinformatics and still heavily used until today, okay? Called minimizer seed. Very simple algorithm. However, it's still very hard to count the number of minimizer seed that you would get. It's still very hard to predict a lower bound on the number of minimizer seed that you would get. In some of the cases, you would get per window single seed. But in this example, we are not getting per window single seed, right? Some of the windows we got seeds, some other windows we got nothing. Because it's still the exact same seed stored in there, so we just ignore, right? So that's why there are still a lot of research trying to predict what lower bound we could get out of this. And this is specifically good for mathematicians. They try to always come up with tighter lower bound on the number of seeds that we will get. All right, now let's continue. I guess until maybe here, we don't have A's except this one. So this one's still dominating until we arrive to here. This is 2 A's. They will start dominate over that guy. And then we start having it. Now, the good thing that this one, I think we already have it, which is this, but now with different starting location. Because this guy start at location, I don't know, this is 10, so this should be 10, right? Because this starts from 0, and then it should be 10, or maybe plus 1, 11. So if we have different location, we store both of them. But if we have the exact same seed, the exact location, we ignore the second thing. We just store it once, okay? Hopefully this is clear. So it's very hard to see repeated entries in this table. We could have the exact same seed, but different location, that's fine. But it's very hard to see the entire 2 columns, exactly the same thing. No duplicates record should be there, okay? Now you could follow this in your own at home and see if it is correct or not, right? Now, at the end, this is what we will get as list of minimizer seed. And if I ask you a question, what would be the hash table? This is the list of minimizer seed. What would be the hash table we discussed last time? The hash table was 2 columns, right? The first column, there was one restriction, which is very important. Do you remember what it was? We cannot record the same k-mer more than once in the first column. Cannot be any duplicate in the first column. You could have whatever you want number of location in the second column, but the first column should always have unique entries. Okay? What does that mean? Let's erase here. So now the hash table will be 2 columns, right? The first column, we said it's the seed itself or a hash value of the seed. Seed itself or hash value of the seed. But for simplicity, let's consider the seed itself. And practically, normally it should be the hash value. Okay? And we discuss why. You remember why we use hash value, why we use hash function? Excellent. The length of the seed is different from one application to another and depends on the user to choose the K value. So he could choose 10, 20, 30, 200, 1,000, and so on, right? In order to make this unique and ease or facilitate the application, the data structure that you are going to define, we should fix that length. That's why we convert whatever the length is using a hash function to a specific number of digits as a numerical value, okay? So now, here we are going to store the k-mer itself. Now, remember, no duplicates. So how many entries should be here in the first column? 2, excellent. What they are? Excellent, the first and second, and no duplicate. So we ignore the third and fourth. So we record the first one and the second. Now, how about the second column? 0 and 6, excellent. So 0, 6, and 5 and 11. Excellent. That would be our hash table. Okay, let's see. Right? Is it clear how we convert the list of k-mers into a hash table? So if I ask you in the final exam how you convert this into this, would be easy, difficult? Yeah, I know, no final exam, right? All right. So yeah, it will be more fun if you deal with those algorithms in your own research. So normally, people consider this as a cryptic thing. As a black box, you just call the algorithm, give me the seed, query the index, that's it. You don't build it your own, right? Yes, please. Normally, you should use hash function. Normally, you should. That's why we call it hash table, okay? And it will be really beneficial to use the hash function, especially if you want to control the collision rate we discussed last time, which was your classmate question last time. If we want to control the inexact matching, inexact. We are not looking for the exact k-mer to be there in the hash table. We want to allow some differences. How we can do that? Then we could play with the hash function, or we could play with the seed itself. Like ignore the second character all the time. This way, you're always allowing inexact matching using exact matching approach, right? So it's always beneficial to use hash function, especially if we grow with the size of the hash table. Yes. Excellent. I have a few slides on that. So let's just wait a bit until we arrive to those slides. But hopefully everything's clear now how we extract those minimizer seed. So we said we will follow the overlapping k-mer algorithm exactly as is, no change. And then we divide those k-mers into groups. Here we choose to be overlapping groups, and the size of each group is W, which is 5 in this example. And then out of each group, we do some kind of sorting. Here we use lexicographical order, which is alphabetic sorting, basically. And then we choose only the first one out of each group. And then we list them over here. We build the hash table on top of that. Everything nice and perfect. Okay, now, which is an open research question, what would be the number of minimizer seed that we could extract? So the ultimate goal of minimizer seed was to extract 1 per window, okay? We already did a great job reducing the number of k-mers that we could extract from n minus k plus 1, which is the overlapping seeds, into 1 per w, right? Each w k-mers, we just choose 1 out of it. However, as we saw in the example, it's hard to extract 1 per window. You can see how many windows we have here and how many seeds we extract from there. Now let's see. What is the number of overlapping k-mers that we can extract? Overlapping k-mers, no minimizer here, just overlapping k-mers, which is this thing, right? N minus k plus 1. N is the length of the sequence that we are dealing with. I think this is 25 or so, right? And k is the length, which is given also in the question, 10. And why we did minus k plus 1? We said toward the end of the sequence, we don't have too many overlapping k-mers. We have only 1 that we can extract. So it's simply n minus k plus 1. Now, what is the number of windows? Remember, we divide this number over groups. We divide this number over groups, and each group has a size of w, okay? But now, how many of those groups we could get? This is the number of seeds that we divide over groups, right? And we have w of them in every group, and they are overlapping. So you can think about this sequence as the k-mer we got, and then we got w of them, except the last thing, we will have only a single w. We cannot overlap too many w's toward the end, which is here. In the last w, right, we just have 5. We cannot choose this as another w, this another w, this another w. So single w toward the end, but we still have the same thing, which is this number, right, minus w of them plus 1. As simple as that. This number, the entire thing, which is here, minus w, because toward the end, we don't want to have w overlapping windows, plus 1, because we have the last one, okay? Which is this number. N minus k plus 1 minus w plus 1, okay? You could do the math, of course, n minus k minus w plus 2. And that will be the total number of windows. How about the number of minimizer seed? I already give you a lot of hints that the expected number, or the worst case, would be is to get 1 per window, right? How many windows we have? That is. So that would be the worst case. Why the worst case? It is clear and maybe best case because we already can define the number of minimizer. But at worst case, in terms of number of seeds, this is excessive number of seeds when we extract 1 per window. We've got a large number of minimizer, and we don't want that. We want to filter them to the minimal. That's why we call it worst case. Now, what is the best case? Which is something like that, right? Something like this. Here we don't get 1 per window. We're not getting 1 per window. We have many windows, and we have only 4 minimizer. That is average case, or let's call it best case, right? This is what we are looking for. Now, how we define it, or how we can calculate it, excellent, very close. If we don't consider overlapping, right? Because normally a seed will remain a dominant within W overlapping windows. And we saw that many times. the same seed, it's still on top of the list over multiple windows, right? Until it's excluded from that window. So it's still in the top of our list, still dominating in terms of lexicographical sorting, right? Over W windows. And then those W overlapping windows, just ignore, no effect. So we can ignore them. In this case, it says if we consider non-overlapping windows, and one pair non-overlapping window might give us something. But in fact, not one per window. They said, let's choose two per window to be on safe side. Two per non-overlapping window, okay? Or in reality, maybe I can draw on. Yeah, in reality, I want those non-overlapping, right? This 5, 1, 2, 3, 4, 5, right? And now another 5. So group W of 5, W of 5. And then I want to take 5 in the middle. Okay. Now in this way, within those two windows, this and this, I want to pick 2. So it could be 1 for this and 1 for that because span longer area than this, right? And that would be the average case. Let's see. So they divide over W because they don't want overlapping. They want non-overlapping. That's why they divide them into W groups. Each is a group, because non-overlapping. Forget about the +1 because it's related to toward the end again. We might not have a full group of W windows or W k-mers, sorry. So that's why we add 1 just for the fraction to add up. And then we multiply that number by 2 to cover this case. But this is still very loose lower bound on the average case. It's very loose. And there are some research papers replacing this number by 1.5. 1.5. We're getting 1.5 k-mer or minimizer over 2 windows. Now, what does it mean, 1.5 seeds? How we can divide the seed into 2 halves? This is average case, right? So sometimes we'll get 2, sometimes we'll get 1. On average, it's 1.5, right? However, as I told you, since that paper went away, which is 2003, until today, we are still getting every 2-3 years a paper showing a tighter lower bound on this number, okay? So let's agree that this is still a loose lower bound on the number. Now, if you want a tighter one, this hopefully, we don't need the board now. Yes, the average, we cannot, until today, there is no equation about the best case. The best case should be the minimal number that we could get ever, okay? It's hard to predict because some windows will provide minimizers, some other windows will not provide, okay? And until today, I don't know if there is a paper showing that. We have 2, 3 from math department in the class, right? So maybe you could come up with a tighter equation for that. And this hopefully give you some glimpse about the number of works that try to come up with a tighter lower bound on that equation, okay? So each of those plot is an equation or research paper try to show that effort, okay? Until this year, so this is 2025, last month, this paper tried to show the tightest lower bound that they could come up with, which is the red plot over there, okay? So this is the thing that we were discussing, which is ×2. And then after a few years, they show it as 1.5. And then later on, they try to predict it with different equations, okay? Right? This is a bit complex equation. I try to summarize it. It will be, I think, difficult to go into that detail. So if you're interested, you feel free to go to the paper and read it yourself, right? However, what is important to us is to know at least the worst case, which is easy to understand, okay? Any question? Any question? You already had really excellent question. I'd like to encourage you always to keep that pace. It's very nice to ask this question because most of them are research questions, okay? Now, your question. What value should we use for K and W, right? Now let's see that example. We have a sequence. We have a sequence over here. We have the exact same sequence over here, but we change one character. We replace the C over here with the T, okay? And now we are following the minimizer. So we have all overlapping k-mers of size 3. K here is 3, okay? And W is 6, all right? So we choose 6 overlapping k-mers, and we choose one of them, which would be ACT. And then the next 6 k-mers, and the minimal one, based on lexicographical order again, ACT. Now, you could ask me a question, what if we don't want to use the top on the list? We want to use the least on the list. For example, A, C, A, B, C, D, E, F, G, H, I, J, K. I don't know what would be the last one on the list. Maybe T? Yeah, T, I think, right? So instead of picking always the A, I want to pick the T's, okay? That would work. How about when we convert to hash value? I don't want to pick the minimal or the minimum value. I want to pick the maximum value out of the list. It would work. Whatever you could use over there, it's up to you. By the end of the day, it's the evaluation who's saying that this is better than that or not. What do we mean by evaluation? First, I want to extract the minimal number of seeds all the time. Which method give me the minimum number of seeds? Second, minimal number of seeds doesn't always mean it's a good choice. Because if I am losing what we call sensitivity, what is sensitivity? What is sensitivity? It means my detection mechanism is sensitive to things that already exist in the sequence. So imagine you have a sequence, you just copy a subsequence as is, so the entire subsequence already exists in that sequence, and you use it as a query. Will your algorithm find that query in the original sequence or not? If it is able to find that sequence, it means your algorithm is 100% sensitive. If it is not able to find that query in the entire complete sequence, your algorithm is 0 sensitive. So extracting lower number of seeds is not always good because you might lose sensitivity. You might miss some of those query, although we already know in advance that they exist. Okay, so this is another very important metric when we evaluate those algorithms. And if you have one of your project or review paper on seeding, you have to do that. Okay, part of your evaluation results should be on sensitivity, should be on index size. What is the size of the hash table? Is it huge? Which is directly correlated with number of seeds that we extract. If you extract too many seeds, your hash table will be huge. If you extract fewer, it will be less, and so on. Okay. The other thing is the execution time. How long it takes your algorithm to generate those k-mers. If it's taking too long, that's not good, right? Now let's go back to the example. I hope it's clear now, just an example of minimizer seed over here and over there. However, the catch in this slide is that we are using very similar two sequences, right? The only difference is one character, and we are using certain values for W and K. However, when we check the minimizer seeds that we extract in both examples, you can see that the first and second, they are exactly the same. But the third and fourth, they are totally different. That is to say, half of the minimizer seeds now are mismatching each other, although we make one difference. Okay? So we have to pay attention to that. And this will be what is important for the decision for your algorithm to make when they try to recognize whether those two sequences are similar or not. If I'm finding half of the k-mers or the minimizer seeds are not matching each other, I should account for how many mismatches I could handle. Okay? And we discussed last time why single difference caused that a huge number of differences between the minimizer seed, right? It's related to when we start having overlapping seeds over here, that mismatch, how many overlapping k-mers going to affect. So you can think about k here is what value? 3, right? So you can see the k value is 3 from here. So we expect at least 3 k-mers to be mismatching because of that difference, which are overlapping over the t. So those 3 k-mers should be different from the 3 k-mers. And in fact, they are. They are. Maybe the last one is not. Maybe those 3. Yeah. So at least we have 2 of them different. So we have CTT, CCT, we have ACC, we have ACT, we have TAC and TAC. Now, why we didn't get 3 exactly? Yes. Excellent catch. Yeah. So this is wrong. So probably we can contact the author of this paper. Just ask them to correct it. Yeah, I was wondering why it's not, but sometimes it happened to not have that difference because sometimes just have random sequences over here. So it could be some other, it could be the 3 k-mers that are affected, shifted to the right or to the left. So it could be those 3, or it could be those 3 impacted by that change. It depends on the location of that character. Okay, but that's a good thing. We should correct it also in the slide. So this should be TTT, 3 T's. Okay. Is there another mistake? Maybe it's going to affect this. No. Bottom right. Oh yeah, this should be also 3 T's. Oh, last 2, all of them wrong. The entire figure is wrong then. All right, but you got the idea, right? That even if this is 3 T's, still the one that we are going to choose, hopefully it's also correct, is the one that starts with A. How many starting with A? Those 2, right? Now, both of them start with A. What is the next character? T and C. C comes first for T, so that should be the minimizer. And yeah, that's correct. ACT is the minimizer C, okay? And now because of that single change over there, we are missing those 2 minimizer seeds. Now, all right, good so far. Now let's change the W from 6 to 8. K is still 3, but the W now is changing from 6 to 8. Now let's see what happened with the minimizer seed. Now, since the window is spanning longer, and we choose 1 out of too many seeds, then the number of extracted minimizer seed will be less than what we got over here. Okay, because now the group size is huge, and we are replacing many of those k-mers with 1. That's why we are reducing the number of minimizer seed. And now if we check, hopefully those 2 are correct as well. But when we compare them together, none of them matching each other. None of them. Okay? So although the 2 sequences are exactly the same, just that character is different. Now, none of the minimizer is the same. So your algorithm might be perfect, your data is nice, but the parameter you choose is making all the trouble, right? So if you choose W of 8, you're not going to capture any similarities. you are going to miss most of the similar sequences. But if you choose a small number of W, you might get something out of it. Now that, again, open the same question, then what value I should choose, right? So based on the recommendation of a tool called Minimap2, which is one of the most famous tool that perform read mapping, is recommending the following. The W should always be 2/3 the K value with a ceiling sign, because we cannot have fraction number. It should be a natural number. It cannot be 0 as well, right? So it should be natural number or integer. Is 0 integer? Right? So that's why it's natural. Natural excluding the 0 from the integer, right? So the W is recommended to be 2/3 the K value with a ceiling sign, all right? Now, it's also not as simple as that, because it also depends on the data that you are using. So if the sequence is very short, it doesn't make sense to use the exact same parameter for things that is 4 million long, as in ONT. ONT is really long, right? Could be somewhere between 200 or 100 or 20 sometimes, all the way to 4 million. But the Illumina is fixed 100, 150, or 300, right? So that's why it's recommended to use also this parameter if you know what you are handling. If you are handling only Illumina, then use a K of 21 and W of 11, okay? If we are using hi-fi, what is the range for hi-fi data? Do you remember? You can get the +1. What is the range of hi-fi data? No ChatGPT. What is the range for hi-fi reads? The read length? 4 million. Still a bit far. Increase that number. 500 million. It's actually less than that number, way less. No, way less than that number. Way less than 4 million. 200? 100,000, wow. No, still less, way less. 25, but 100? No, hi-fi is somewhere in the middle between Illumina and ONT. So it should be less than 4 million and more than 300. So hi-fi this year is different from the definition of hi-fi before 2-3 years. Okay, why? Because now we have the ONSO machine. ONSO, what is doing? Generating short reads, right? As short as Illumina. So before 1-2 years, if I ask you what is the read length for hi-fi, it should be well known, right? Which is somewhere between 10,000 to 30,000. But this year, if I ask you what is the average read length for hi-fi, you should ask me, is it short or long reads, right? So short is exactly the same as Illumina. It could be 100, 150, or 300, okay? But the long part of it, still the old story, which is 10,000 all the way to 30,000, okay? All right, so yeah, when we talk about these 3 data sets, you should use those parameters. And if you ask me this K and W value for hi-fi, is it for short or long? This is for long, because this tool was proposed in 2018. So that time we don't have the accurate short reads, but they might update, or you might do it yourself. You test the hi-fi short reads, okay? And you may find like this is also applicable to those parameters, or this one might be also good enough for both of them, hi-fi short or long. If you find that good parameter, you could contribute to the Minimap2 GitHub repo. Okay, so you could request some change over there, and then your name will be there. Right? However, there is another more recent paper All right. This is a very recent paper that tried to come up with a better K and W value. They claim that the default K and W value that we had in the previous slide were really loose. So we are losing performance. We are exceeding the requirement for storage, for time, for sensitivity, and so on. And we could use something tighter that is going to save the storage and execution time and safety and so on. Sorry, sensitivity and so on. Okay? So they had some suggestions based on the divergence. What is divergence? Is the similarity between the two sequences that you are studying. If you are studying a human to human, you consider the differences to be very minimal. You just account for the genetic variation, the disease, and the inheritance coming from the parent, right? But if you are studying a banana and a human, you consider to be a huge differences, right? So based on that, and based on the read length, we could have different value for K and W, okay? And again, this is based on the practical side, not the theoretical side. They have many data. They control the divergence. They control the length of those sequences. And then they vary the K and W. They try all different Ks, all different Ws. And then they come up with this number, which provides some balance between the sensitivity and whatever computational requirements are there. Okay, like storage, like the index size, and execution. Okay, so that is still a difficult question to answer. They can provide like practical values, but they cannot be 100% sure that this should be the value. So you may come up with a tighter value for those as well. You may evaluate it yourself. Again, here, they were not using the hi-fi short data, so that could be one of your contribution. You could evaluate those most recent data, and they come up with different K and W values. Any question? All right, no question. Now, can minimizer seeding be improved? What are the things that we can do more on top of minimizer algorithm to improve it? We're not proposing new algorithm. We're still in minimizer seeding, but we want to do some little tweaks here and there to reduce the number of extracted minimizer seeds. All right. This is a bit old paper, 5 years old, published in 2020, called Weighted Minimizer Sampling Improves Long Read Mapping. This is a very important term called weighted minimizer. So now we are not extracted only minimizer seed, but we are extracting a seed with a weight value. So we are assigning a weight to each of those minimizer seed, and based on that weight, we're going to choose which one to pick. All right? Now, why that is important? Now, they claim the main weakness of minimizer-based indexing is the possibility of very frequently occurring minimizer. And we saw that already in practice in the previous example. We saw that one seed appears many times, right? And not only the same seed with the same location, but also somewhere else, we start getting the exact same seed, but with different location. So both of them, we call them, both of those cases, still like increasing the frequency of that k-mer. And we are getting the exact same k-mer multiple times, right? This is what we mean by frequency. Now, why that is a problem? Think about the hash table. For the first column, it's not a problem because we don't have any duplicates, right? So we're still recording the exact same seed once, even if it's happening like 1,000 times. Now, in the second column, you start seeing the problem. You start having a list of location that is really long. You start having like million location for the exact same seed. But for the other seeds, we have a small number of lists for those locations, right? Now, again, why this is a problem? Why if we have like increased frequency for those seeds could be a problem? Excellent. That's going to create some issue with the balancing, especially for the cache. It's going to create issue in computation. So the cache cannot handle those situations good way because you are going to load this entire list of location to the cache. If it doesn't fit, then you are going to have gradual visits or multiple journey to the DRAM to fetch all those locations to the CPU in order to process them. But there is also a problem with the sensitivity itself. Now imagine I have that seed in the query. How many times I need to visit and check with all those locations? Now, if I have a million possible locations in the sequence, and I got a query with that seed, then I need to visit all of them to verify, does really the entire query exist at each of those locations or not, right? And that's going to create a problem for me, which I call a false positive problem. So false positive means the seed might exist, but the query itself does not exist because the seed is just a subsequence. But the entire query might not exist as a complete sequence. But the seeds itself exist many times, like million times. But when I check the other seeds coming from the other part of the query, none of them exist, right? And that's what we call false positive. So the query itself might not exist at all in the genome that I'm checking, but some of those seeds extracted from the query exist and more frequently than others, right? And in this case, I have like million potential possible location in the genome. I have to go to each of those and verify. Okay, I have the seed there, but how about the rest of the query? Does the other queries exist? If you remember where we color those pieces, we had the blue followed by green, followed by yellow or red maybe. Remember this. This is the process that where we need to go to each of those locations and verify the other part of the query. All right, so hopefully this is an important problem. Hopefully you understand what we are talking about here. Now, how they solve it? How they solve that issue? Remember, the problem is with the most frequent k-mers. The problem with the most frequent k-mers. So their goal to minimize those frequently or frequent k-mers. And what we mean by frequent k-mers that they are the exact same seed appearing many times over the entire genome. Okay, so they just add default weight value to each minimizer seed. Let it be 10, for example. Okay, whenever they hit that k-mer again, like they find it again in different window, they reduce that weight. They hit it again in another window, they reduce that weight. Now, over the span of several bases or several characters, now that k-mer, the most frequently one, will get a very minimal weight value. And the rest of the seeds still with very high weight value. Then they could now impose kind of sorting, give me the best k-mers with weight of higher than that threshold, for example. Then they ignore all the seeds with a weight less than a threshold. In this way, they're already ignoring the most frequent ones and keep the other k-mers in the hash table. Okay, so that is minor tweak, small addition to the minimizer seed, but it's important, especially when we have large portion of the genome repeated. Okay, especially in human genome, we have about 50% of the human genome just repeated itself, right? Just repetition, right? And in this case, wherever you extract k-mers from this region, they will appear again, again, and then again. Okay. But other than that, you won't feel the difference. You won't feel really there are differences in terms of the extracted k-mer. So they show some evaluation for this method. This 3 different data sets use W of 10, 10, and 50. And that's going to show huge difference in terms of execution time and in terms of memory, why execution time is becoming less. Because as you go, you block that k-mer from appearing again. So you save some storage or execution time to store that seed. You save some time also to calculate the sorting for that k-mer. Once you see that k-mer, you don't sort based on lexicographical order or hash value. You just ignore it, right? So hopefully that's going to save some time. Plus memory, of course, because you are removing that from the index size. Okay. Now, you might ask, what if we do all this process after we complete the complete hash table? Think about, you complete the entire hash table, you calculate everything, and then you start filtering some of those seeds. You just remove it from the hash table. Now, that might be good, might be easier to apply for minimizing seed. However, you may not gain execution time benefits because you do it toward the end. You already calculate everything. You already include everything. You already do the sorting, and you pick that seed. You find it most frequent, and you're still adding to the hash table. But that's might to save the hash table size. So you might get some benefit from the second portion of the data, but not those results. Okay. Now, this year, a few months ago, in 2024, we see a bioRxiv paper. bioRxiv, by the way, means a preprint. So nobody review it. We don't know the accuracy, the correctness of this work. So someone could publish anything on arXiv or bioRxiv. arXiv is the general server for having the preprint. bioRxiv is just dedicated for biology, biomedical, and so on. Bioinformatics is part of bioRxiv. Okay? But you still could publish in arXiv and bioRxiv. It's for free. You can submit whatever PDF you want. They only have dictation for example, is it relevant to the server? And you're going to choose some category. Does it belong to computer science, to machine learning, to bioinformatics, security, and so on? They will dictate that. They will check, does it belong to this field or not? But other than that, they don't care about the accuracy and correctness of the results. You can still post whatever you want. It's for free. The benefit, they post it within 3 days. So within 3 days, you get approved. And the nice thing, why we do that, I'm doing it myself. Most of us, we are doing it. Why we are doing that? Because some of the publisher, like journal conferences, might take 6 months to accept your paper. Might take a year, 2 years, right? While waiting, you might get scooped. Scoop means someone else published the exact same idea, the same work, but with different data, different results, and so on, but the exact same idea. They could publish it sooner than you, and then they got the credit over you. Although you were the first, but nobody knows about your work because it's still under processing with that journal. So it's always good when you write a paper, you submit it directly to arXiv, bioRxiv. You don't care about completeness. Don't look for perfection. Just submit it, and while it's in there, you could keep submitting the second version, the third version, the 10th version, the 100th version. You could keep updating. Doesn't matter, okay? And while we are waiting for the response from the journal or the conference, you already got the credit for it, okay? Now, that was a side story. Anyway, so this is a very recent paper. Try to build on top of the previous paper. Try to control the frequency, but now they don't want to fix the K size. They use the K initially, like 10, 15, whatever value you want. But whenever they find it as very frequent in the table, they don't ignore the entire row. They don't delete the entire row. That is the most frequently K-mer. What they do, they just keep increasing the length of the K. They query length of 10 characters, and they find it very frequent. Now, okay, let's increase by 1 character. Let's make it 11 for the same K-mer. Now, when I increase the K from 10 to 11, what do I expect? I expect to reduce the frequency. Why? Because now, yeah, the first 10 characters, they exist in multiple locations, But now when I consider 11 character, some of them might still there, some others might not match because might end with T, but what I'm looking for is ending with A, although the same first 10 characters still there, right? So this is exactly what it's about. They try to use variable length seeding for solving the issue with the most frequent one. They said the most frequent ones, not necessarily to be bad, that's why we're not going to ignore it from the hash table. We are going to break down the problem into sub-problems. What if we consider A toward the end rather than C, G, T? Is it still getting high sensitivity or not? All right. Do you have any question? Now, I always like in my courses to include some part about the research itself. That's why I'm giving you all those ideas about every topic. Most of them really very recent paper. Why is that? Because all of you masters and PhD student and part of your research to develop something new. So hopefully those going to open some doors for you, how you think about improving something. Sometimes those changes, yeah, they might be incremental, like tweaking something, changing something, using different values of K and W and so on. But sometimes it might lead to something totally different. Like, think about the minimizer. So far, most of the people are still relying on the hash value, sorting that hash value and picking the minimum hash value out of the W k-mers. Now, what are other alternatives that might be better? What could be a better way of choosing some seeds out of many seeds? Think about it. You might come up really with totally different algorithm that might use machine learning or something where you already know that those region of the genome might be difficult to handle. Let's use something else over here, but other region of the genome, easy to handle. Let's use something less computationally. And then we will have some hybrid mechanism to handle those genomes. Right, if you don't have question, maybe we can jump on the implementation side of this algorithm. That hopefully going to give you something to play with. If you have something like implemented algorithm of minimizer, then easy for you to play with the K values, W values, tweak the algorithm and see if it works better way or not. Now, the first implementation, of course, it's always hard to read the code from slide. It's better if you have it in editor and then you can visit each of those variables, play with it. But you already have it in the slides in iCollege, so you can copy it, paste it to a file, and then start executing it and so on. So how we implement that, it's really easy, straightforward. You have a for loop over the sequence. You start from the first character, you pick the next 10 characters, and you save them somewhere, okay? Then you increase the index by 1 to the next character, you pick the next K character, you store them somewhere. But be careful that we are always looking for something as minimal in terms of something, like lexicographical order or hash value. Instead of storing all the W values, right, and then sort them and then pick the one that is minimal, you could directly, whenever you have two candidates or a pair of those k-mers, sort them and pick one and store it somewhere. You don't need to store two of them and then move to the third, store the third three, then store four of them until you arrive to W value and sort all of them and then pick one. You don't need to do that. Every time you get a new candidate, you compare it with the previous best candidate, not with all of them even. Just single best you need from the entire group. Every time you get one candidate, just compare the best from this group with the new coming. Is it better? Is it lower value of hash value or lexicographical order or whatever? Okay, and then choose that one if it is still best. Okay, and then move on. That is the only idea they have in this code. Okay. All right. Now that algorithm I copied from the 2003 paper. So it's very old implementation, and it's not for genomic. Remember, this is for documents, any PDF document. And instead of K or seeds or minimizer seed, they have fingerprint. The term is fingerprint called, okay? But still the exact same concept. Now in this implementation, this is coming from Minimap 2. So this is related to genomics now. This is the algorithm that exactly we use in genomics. So if you're interested in running efficient algorithm in genomic data, you should use this one, not the previous one. But the exact same concept, nothing different, okay? So this is publicly available tool called Minimap 2, and that is the function exists in Sketch file in that tool where they handle the minimizer seed. And the exact same way, they have a for loop that go over the sequence itself. Every time they face K character, they bring them in and so on. The only catch in this code is that you don't really need to look for K character. You really don't need to do that. Why? So now, okay, for the first K, yes, you might need the K. But now, when you move to the next K, what is the difference between this and this? Excellent. It's really this guy. This is the added one, and this is the excluded one. So we exclude one, we add one. So you already have those 9 characters. Why you need to do computation again and pick them from the sequence? So every time you read one character, you just add it to the sequence, exclude the part from here. You got the entire k-mer, right? That's the only catch in this implementation. So that's going, yeah, really, it's going to accelerate the thing. You might think those little tweak might not impact your code, but in fact, it is, especially if you are doing it for too many things, too many iterations. Think about 4 million long sequence. You are doing that, a little saving here and there and there and there. By the end of the day, you will have large saving in terms of execution time. So what is the best way or data structure to implement this idea? To bring one character from one side, remove one character from other side. What is the best data structure that you could use? Q. So the problem with the Q and DQ, you always don't forget this. You are washing some dishes, right? And you are stacking the dishes on top of each other, right? Now you do Q, you add on the top, DQ, remove from the top. So we don't want such thing. We want to add from top, remove from the bottom. Sometimes they call it double side Q. So they can read from here, remove from there, and so on. So we want that kind of data structure, okay? So here you got a C implementation, which is the most efficient thing that you could do if you're looking for high performance. But here I'm providing also Python implementation for you, if you're interested. This is in my repo, my GitHub repo, but it's doing something similar, but at high level. You don't care about the character level of those because Python can handle that. Of course, if you write in Python, don't expect to compete with C. That's not the case. You'll never compete. You'll never win the race. Why is that? Let's look for this example. This example tries to compare the performance that you would get out of multiple programs written in different programming languages. Okay? The problem is still the same, which is matrix multiplication. So you got a matrix. You want to multiply it with another matrix. Okay? And to solve this matrix multiplication, you need 3 nested for loop. 3 nested for loop, as you can see here. 4, underneath another 4, underneath another 4. Okay, all of them nested. Nested mean I pick the first index from here. I need to finish to complete the entire for loop here, and then I can proceed and increase the index over there. Likewise over here. I pick one index here, complete the entire number of iterations in the for loop over there, and then increase the index over and over. Why I need to do that? Just to refresh your mind about matrix multiplication. So to solve matrix multiplication, you have a matrix, another matrix, you multiply them together, you get new matrix, okay? How you solve it? You pick the first row times the first column. First row times the first column will give you the first cell, only the first cell. How you do it? You get 1 times 7 plus 2 times 9 plus 3 times 11, give you that number, okay? Now, you go to the second row, multiply by the first column will give you the second element over here. The third row over the first column, still continue with the first column over there. Now, if you want to solve this one over here in the second column, you go with the first row, but this time with the second column. Then going to give you that value, and so on. This is just to refresh your mind, okay? Now, think about you implement that algorithm, which is 3 nested for loop, in multiple programming languages, okay? Exact same idea, no tricks, nothing, no optimization, and so on. If you implement it in Python, you would get that execution time, okay? This is the easiest. We always pick Python because easy to write, right? Something human understandable. If you go with Java, you reduce a bit that execution time. If you go with C, you get the best performing out of those programming languages. If you start now over here, you do some tricks on optimizing, parallelizing that code. For example, instead of performing the for loop, you wait for the next iteration, the third iteration. They are really independent of each other. For example, why I would wait for this cell to be computed if I can compute this cell also independently of this. For example, if I want to compute this and this together, I get the first row multiplied by the first column and the second column. I will get both values together at the same time. I really don't need to wait. There's no dependencies between the values. They are independent of each other. And that's why I don't need to wait for the entire for loop here to be computed to move to the second cell over there. So I could parallelize those elements. Instead of doing one over another iteration, I could have parallel loops, divide and conquer. How many of you know about this concept? Divide and conquer. Divide and conquer means if I have this row and this column, and imagine this row is 4,000 long, okay? And this column is 4,000 long as well. 4,000 elements need to be multiplied by each other, and then you add the summation together. Now, you could divide that matrix into smaller submatrices. Okay? For example, you have a row of 4,000 elements. You can consider every 100 elements aside as a submatrix. Okay? Now, you could multiply those 100 or 1,000 together with the other elements from the other column, and then you add summation of those and keep it aside. You go to the other submatrix, solve it, and keep one value aside. You do the same thing for the third submatrix and keep it aside. Now you have 3 values from 3 submatrices. If you add those numbers together, you'll get the total number, which belongs to the complete row over there. And that's what we call divide and conquer. It means divide the problem, the bigger problem, into sub-problems that you can solve each separately, and then you add up the result. Okay? This is a very famous concept if you are looking for high performance. And then there are the hardware side. All of this is still software, okay? And those two are hardware. What does it mean? Vectorization. Vectorization. So in some Intel processors, there's something called SIMD. How many of you study computer architecture course? One? Yeah, Bilkent student, they should study all of it. You're from MIT2, right? MIT2? UT2? Sabanje. You should study. No, this is computer engineering. Okay, yeah. There's a concept called SIMD, single instruction, multiple data. Single instruction, multiple data. What does it mean? It means if you are looking for 5 plus 3, and then 2 plus 1, and then 6 plus 7, for example, how many addition instructions? There are 3, right? So you will execute them as 3 lines in the code. You will execute this first, then the second, then the third. The SIMD says if you have the same instruction over multiple lines, you could combine all of them together. So that's why you have single instruction, which is the addition, and multiple data. You have 3 variables, and 3 variables need to be added up. How you do that? There is a vector called SIMD, normally 128 bits or 512 bits. And recently, they replaced it with something called AVX. AVX 512. That's the length of the vector. What you do in the vector, you consider, for example, the first 8 bits for the first number here, 5. And now, next number 2. And now, next number is 6. You bring another vector. You add the other side of the equation, which is 3, 4, and 7. Now, you have 2 vectors. You do the add operation to those 2 vectors. So you add the 5 plus 3, 2 plus 4, 6 plus 7 in one instruction. So one equation, directly, you add all those numbers together. And think about this 512 bits, so it can fit more than 3 equations. So you can add maybe 8 numbers, and you can add them all together in one instruction. Now, why I reduced the 3 instruction to 1? What benefit I would get? Remember, each instruction run on your CPU takes 1 cycle, 1 clock cycle. So if your processor running at 3 gigahertz, which is most of your CPU should be around 3.5 or something gigahertz, that is the speed each instruction should be executed. Now, instead of waiting 3 clock cycles, you just need 1 clock cycle to execute that addition. That's why this is going to provide some benefits in terms of vectorization. Okay, that's only supported by Intel processors. And other processors, of course, they might have their own techniques to accelerate. The catch I want to highlight over here, the speed up that you would get out of those techniques just by changing the programming language, doing some optimization. This is how you could make your algorithm really fast. And now with the help of AI or those LLMs and so on, you could get like some of those techniques implemented in your code without really need to know the details of those approaches. All right. Do you have any question? Any question? I like to really visit those topics, especially it's not really related to bioinformatics, but you are a grad student, you're not undergrad. It's always good for you to study those side topics. It will open your mind, it will help you a lot in the interviews, for example. It will be really big difference between a student who read only the book and that's it. There is no extracurriculum activities aside. That will be really clear from the interviews. I'm doing it myself with the candidate that I'm interviewing for PhD student. I ask about these things, not necessarily the hardware side and how you accelerate algorithm, because this is not part of the position I'm looking for in the student, for example. But there are other things that you should really be aware about. For example, data structure, algorithm, how you calculate the runtime complexity, how you make an algorithm more efficient. Algorithm doesn't mean software. We're not talking about implementing a software. Algorithm means a way to solve the problem. Think about the minimizer, just algorithm, right? Group them into WK-mers, pick one out of those groups. That description we call as algorithm, okay? You don't need to implement. You don't need to have a software out of it. Just algorithm, a way of solving that problem. And there are a lot of examples from Google, Microsoft, Facebook interviews. You could check yourself. You can see what kind of interviews they have. They give you a problem. They ask you to come up with a solution, for example. Okay? So please take care of those things. It's really nice. Not necessarily the book itself or the curriculum. Excellent. For example, Java. What is the most famous thing about Java? something really unique. You might not find it in any other programming language. Something called JVM, Java Virtual Machine. What is that? What is it? That is something to isolate the hardware from the software. In a sense, if you have a Java program you want to execute in this machine, I compile, I run, I execute on the machine. That's nice. Now I want to move the same code on another machine. Do I expect to get the exact same thing or not? The Java virtual machine going to isolate the hardware from the software. So whatever you have as hardware, whatever you have as a processor, Intel, AMD, and so on, it doesn't matter. You still can run the exact same program without executing again, compiling again on the different hardwares, and it will give you the exact same performance. So JVM going to understand what kind of hardware you have and translate your instructions into the underlying hardware. That is something unique from other programming languages, because if you have a program written in C, for example, it's already compiled. You want to execute on something else, it will give you some errors. This processor, this instruction, this something does not exist. I don't understand what kind of hardware you are using. You need to recompile, re-understand everything going with the other machine and so on. So that's why we call this as a portable code. And this come up with overhead. It's always going to make your software slower because this kind of translation. So translate your code into something independent of the hardware, okay? That's one of the overhead that you're going to lose. But other than that, yeah, for example, if you know that you are solving an issue in biology, right? And you expect all the biologists to be familiar with R, MATLAB, or Python, right? This is the norm. Most of the biologists understand those three languages. If you write your code in C, you don't expect the biologist to build on top of your code, or to improve your code, or to cite your code. So that's the thing you might lose if you are building something in odd with what is a common sense in that area, okay? Either sometimes they provide what we call a wrapper. A wrapper means you build an interface in any other programming language, and you are calling your code from different programming language into that programming language. For example, you can use C and C++ together. You can use C and Python. You can use a Python and C all together in one program. That's a wrapper. You build, and you can call different parts of code from other programming language all together in one piece. The other thing on top of this is the package management. So you build the software, you would like to run it on someone else's computer, but once you start installing it, you see some missing packages that you were using in your code. All of you, maybe you were using in the programming assignment some packages, which is maybe not allowed, right? In the programming assignment, you're not allowed to use some packages or libraries from somewhere else. But if you start using that and it's missing from the computer that you are executing your code on, your code directly complain about that. The way to solve that is to use Conda, for example. Conda means I'm going to get your software plus all other libraries that you need for your code all together in one place. Now, if you move that package to another machine, you already have everything inside as one package. So you will never face issue with packaging, with the missing package, with conflicting packages, and so on. That is the Conda concept. Then now we start seeing most of the software not only as a raw code on GitHub, but we also start seeing the code on Conda. Conda is way easier than GitHub. You download the code and build from scratch. You face some issues. You need to download another software, build them together, and so on. But Conda, just you download the package, run it. You don't need to install the code. You don't need to do anything with it. It's already ready with all the dependencies. That's it for today. I think next Monday we won't have lecture, right? It's a holiday. No? I think it's a public holiday. Really? It's not a holiday? Okay, I'll confirm and I'll let you know over iCollege. If you didn't hear back from me, it means no holiday. If it's a holiday, I will send you some, okay? And we'll continue with the next 2 lectures with indexing. We will take another algorithm that does indexing and see how it's different from overlapping, from the minimizer seed, and so on. All right? Thank you so much for today, and have a wonderful day. We have a class? Okay, then it's confirmed. We have a class next Monday, right? Really? I don't know. When I check public holiday for Georgia State, there is a holiday. It says, what was the name? Yeah.
Just shows in March. There is just spring break in March 17th.
I see. I see. All right.
When you say what is the biggest,
Sorry?
can we use pandas?
Pandas you can use, but the concept of conda is really wider than panda. So I think I said you are not allowed to